Hello students, I am CG sir. Today we will discuss the chapter vector space. So let us first know what is vector space. You have some idea about the field and also vector space. So let V be a non-empty set and F be a field, and we say if any two elements of V, suppose alpha and beta, suppose there is an operation plus such that alpha plus beta is in V. Number 2, for any three elements alpha, beta, gamma in V, alpha plus beta plus gamma equal to alpha plus beta plus gamma. That means the associative property holds. Next, there exists an element theta in V such that alpha plus theta equal to theta plus alpha, and for any alpha in V there exists an element minus alpha such that alpha plus minus alpha equal to theta, and the plus is commutative. That means for any two elements alpha and beta in V, alpha plus beta equal to beta plus alpha. These five operations with respect to addition, and there is an operation that is the multiplication, scalar multiplication. That means for any C belongs to F and alpha belongs to V, C alpha belongs to V. For any two scalars C1 C2, any two elements C1 C2 in F, C1 C2 alpha equal to C1 into C2 alpha equal to C2 into C1 alpha. Next, for C belongs to F and alpha beta belongs to V, C into alpha plus beta equal to C alpha plus C beta. Next, C1 C2 belongs to F, alpha belongs to V, C1 alpha C1 plus C2 into alpha equal to C1 alpha plus C2 alpha, and there exists an element 1 belongs to F. Because F is a field, there exists the identity element 1 into alpha equal to alpha for every alpha in V. Then we say that V is a vector space over the field F. It is known to you, till we should learn some examples, because as much examples you study, the concept will be clear to you. Let us take a field F and V be the set of elements Fn. Then what are the elements? Suppose alpha be an element, then the it looks like x1 x2 dot dot xn, where xi's are taken from F. And if we implement the addition operation on V such that alpha plus beta equal to the pointwise addition and scalar multiplication by the pointwise C into alpha equal to cx1 cx2 dot dot cxn, then with respect to these two operations V will be a vector space over the field F. Example 2, let us take a field F and V is the space of all matrices of order m by n. The entries are taken from the field F. Then with respect to the matrix multiplication, matrix addition, it will form, and the scalar multiplication, it will form a vector space. Example 3, let V be the set of all functions from S to F, where S is any non-empty set and F be a field. Now we define the addition such that for any Fg belongs to V, F plus G of S equal to Fs plus Gs for all S belongs to capital S. That means pointwise addition. And the multiplication, scalar multiplication, is defined as for F belongs to V, C belongs to F, Cf into S equal to C into Fs for all small s belongs to capital S. Then also V forms a vector space over the field F. Example 4, let V be the set of all polynomials over the field capital F. Then also we can prove that as we know the how to the addition of polynomial and the scalar multiplication with polynomial, this will form a vector space over the field F. Example 5, if we take V is the space of set of complex numbers and F is the field of real numbers, then one can easily check that, because we know the addition of two complex numbers and the multiplication of a complex number with the real number, one can easily check that V is a vector space over the field of real numbers. Then there are some simple facts one can easily check, that C into theta equal to theta, where theta is the zero vector in V and C is any scalar of F. Next, 0 into alpha equal to theta, where 0 is the zero element of the field and alpha is any vector of V. Number 3, if we take any non-zero scalar from F, then definitely C inverse exists in F, and C inverse into C alpha equal to alpha for any alpha belongs to V. Number 4, since 1 belongs to F, so definitely minus 1 belongs to F, so minus 1 into alpha, that will be minus alpha for any alpha belongs to V. Fine. Then what is linear combination? Let V be a vector space over the field F, and alpha 1, alpha 2 dot dot alpha n are n number of vectors in V, C1, C2, Cn are n number of scalars in F. Suppose B is a vector which is written in the form C1 alpha 1 plus dot dot Cn alpha n, then we say B is a linear combination of the vectors alpha 1, alpha 2, alpha n. If we change the scalars C1, C2, Cn, we get different types of linear combination of the set of vectors alpha 1, alpha 2, alpha n. Next, subspace. What is subspace? Let V be a vector space over the field F and W be a non-empty subset of V. If further W forms a vector space over the same field F, we call W as a subspace of the vector space V. Now the theorem is that if W is a non-empty subset of V, then we say W is a subspace of V if and only if for each pair of alpha beta belongs to V and each scalar C belongs to F, C alpha plus beta belongs to W. This theorem is important to check whether a non-empty subset of V is a subspace or not, and in some books this theorem is used to define the subspace. Now we'll give some examples of subspaces. First example, let V be a vector space over the field F and W contains only the theta of V. Then obviously W is a subspace and it is called the zero subspace of V. Next we take V as the vector space Fn, where F is any field, and W is taken as the set of elements of V whose first component is 0. One can easily check in the sense of using theorem 1. That means you have to choose two arbitrary vectors alpha beta from W and a scalar C from F. Then you have to check C alpha plus beta belongs to W or not. Okay, you can prove that it is a subspace of V. Number C, let V be the set of all functions from capital F to F, where F is a field and W is the set of all polynomials in V. So definitely W is a non-empty set. One can easily check that W is also a subspace of V. You students, you must check all these subspaces at your home. Next, number D, if we take V as the set of all matrices of order n by n over the field F and W is the set of all matrices of V which are symmetric, then W is a subspace of V. In this in this situation, I want to know what is the symmetric matrix. A matrix is called symmetric if its entries aij equal to aji for all ij varies from n1 to n. Fine. Next, let V equal to C n cross n. That means set of all matrices of complex numbers of order n by n. And W is the set of all Hermitian matrices or self-adjoint matrices. Recall, what is Hermitian matrix? Here the entries of the matrix are complex numbers. So if a matrix is such that A jk equal to A kj bar, then the matrix is called Hermitian or self-adjoint. In this case, W is a vector space over the field of real numbers, but it is not a vector space over the field of complex numbers. Why? Because we know that a Hermitian matrix has the diagonal elements real number. Okay, so if I multiply with I to a Hermitian matrix, then the diagonal elements will be complex numbers, imaginary numbers. So that will not be a Hermitian matrix. Okay. Next example, let capital A be the set of all m by n matrices over the field F, and F is the set of all column vectors over the field F, and V be the set of all column vectors n by 1. Obviously V forms a vector space over F. Now choose X is a particular element of V and W is the set of those X such that Ax equal to 0. That means actually W is the solution space of the homogeneous system of equation Ax equal to 0. Ax equal to 0, it is a homogeneous system of equation and the set of all solutions forms W. Then also W is a vector subspace of V. Fine. You must check this at your home. Next theorem, let V be a vector space over the field F, then one can easily check that the intersection of any collection of subspaces of V is a subspace of V. That means if W1 and W2 are two subspaces of V, then W1 intersection W2 is also a subspace of V. How you can check it? You will choose any two elements alpha beta belongs to W1 intersection W2, then definitely they will belong to each W1 and W2. So C alpha plus beta belongs to W1 and C alpha plus beta belongs to W2. So it lies in W1 intersection W2. So a very easy task. Now choose S be a non-empty subset of V and Wi they are some subspaces of V which contains the S, a family of subspaces containing S. Then we form W as the intersection of all the Wi's which contains S. Okay, then definitely using the previous theorem, W will forms a subspace of V and it is called a subspace spanned by the set S. Further, if S may take the elements alpha 1, alpha 2, only alpha n, then we say that W is spanned by the vectors alpha 1, alpha 2, alpha n. Next theorem, the subspace spanned by a non-empty subset S of V is the set of all linear combination of the vectors of S. That means in the previous case, if S equal to alpha 1, alpha 2, alpha n, then what will be the elements of W? The elements of W will be a linear combination of alpha 1, alpha 2, alpha n. Now take S1, S2 dot Sk are non-empty subsets of V, and then the elements alpha 1 plus dot dot alpha k such that each alpha I is taken from Si is called the sum of the sets S1 S2 Sk, and the set of all sums S1 plus the set of all sum is given by S1 plus S2 plus dot dot Sk. Okay. Now instead of subset, we choose Si as a subspace. Suppose Si equal to Wi, this is a subspace for each I equal to 1 to dot dot k. Then W equal to W1 plus W2 plus dot dot Wk. That means what are the elements of W? These are the elements looking like alpha 1 plus dot dot alpha k, where alpha 1 is taken from W1, alpha 2 from W2 dot dot alpha k is from Wk. One can easily check that this W is a subspace of the vector space V. So till now we know that intersection of two subspaces is a subspace, and this sum is also a subspace of V. But one can note that the union of two subspace is not a subspace. Okay, I give you task to think of example where W1 and W2 are two subspaces but their union is not a subspace, and also to find the example where W1 W2 are subspaces and their union is subspace. Next, okay, here in this case W is the subspace spanned by the unions of W1 W2 Wk. Next we take some examples. Let F be a subfield of the field of complex numbers. What are the subfield of field of complex numbers? The field of real numbers, the field of rational numbers, and there are some others. And we choose V as the vector space F5. Now we are taking three fixed elements, alpha 1 equal to 1, 2, 0, 3, 0 in V, alpha 2 equal to 0, 0, 1, 4, 0 in V, alpha 3 equal to 0, 0, 1, 0, 0, 1 in V. Now S is the set containing the three elements alpha 1, alpha 2, alpha 3. So it is a non-empty subset of V. Now we form the space W, which is the collection of all linear combinations of elements of S. That means W equal to set of alpha, where alpha equal to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3. For all C1, C2, C3 belongs to F. That means these are C1, C2, C3, these are arbitrary scalars in F. So definitely alpha is an element of W if alpha is looking like C1, 2C2, C2, 3C1 plus 4C2, C3. How can we calculate this? Because we have taken alpha equal to C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, and we know alpha 1 alpha 2 alpha 3. So if we put the form of alpha 1 alpha 2 alpha 3, after some calculation we will get this form, where C1, C2, C3 are arbitrary. Next example, let F be the subfield of complex numbers and V be the vector space of the set of all 2 by 2 matrices over the field F. We are taking two subspaces. First, I am not saying about subspace. Suppose W1 is the set of matrices looking like X, Y, Z, 0, where X, Y, Z are arbitrary elements of F. Then you can easily check that it is a subspace of V. W is another non-empty subset of V which contains the element looking like X, 0, 0, Y, where X, Y are arbitrary elements of F. W2 is also a subspace of V. Now we can prove that V is basically the space W1 plus W2, because if we take an arbitrary element A, B, C, D from V, then it can be represented as A, B, C 0 plus 0, 0, 0, D. So obviously any elements of V has the representation of sum of two elements from W1 and W2 respectively. Okay, here you can note that what is W1 intersection W2? It is the set of all matrices looking like x 0 0 0 for all x belongs to F, and this W1 intersection W2 is also a subspace of V. In the next example, I am taking the a field F and V as the vector space of all m by n matrices over the field F. Choose A be an arbitrary element of V, then the rows of A are alpha 1 equal to A11, A12 dot dot capital A1n, similarly alpha 2 equal to A21, comma A22, comma A2n. So in general, alpha I, the ith row of capital A, is AI1, AI2 dot dot AIN, where small I varies from 1 to capital M because there are m number of rows in A. Then alpha I, where it lies, look, capital Aij, these are the elements of F. So alpha I can be considered as an element of capital Fn. Okay, now W, it is a subspace of Fn spanned by alpha 1, alpha 2, alpha m. Now go to example 8. Okay, what is example 8? Look, here alpha 1, alpha 2, alpha 3 are taken as this. So using these alpha 1, alpha 2, alpha 3, we can construct a matrix of order 3 cross 5. Okay, 3 cross 5. How? The matrix is like this. Here the first row is alpha 1, second row is the alpha 2, and third row is alpha 3 of example 8. Okay, so the previous subspace in example 8 is basically a subspace of the row vectors of this matrix. It is called a row space. And the final example, let V be the space of all polynomials over the field F, and S is the set of all elements of Fn in V, where Fn is the form of x to the power n for n equal to 0, 1, 2 dot dot dot. Okay, now since V is the polynomial, so V, the elements of V are like C0 plus C1x plus C2x square plus dot dot dot. So definitely any element of V is a linear combination of the elements of S. So V is spanned by S. Okay, now I end this lecture. Thank you.